To dump the data from your Tromino device, connect the device to your PC with a printer cable and run the Grilla software in admin mode. Click the Download Traces from Tromino button, then click on the Expand button. There are two traces on this Tromino device. I will download the first one by click on the checkbox in front of it and click on Import. It will ask you if you want to create a folder for this trace. I will create a folder called Tutorial. And I will call the site Tutorial as well. And note, the trace will now be downloaded to the database. Once the data is downloaded, you can start processing the data. We're going to use another data I've collected for demonstration. This trace is much longer than the 12-second tutorial trace we have recorded. We can now process this trace by double-clicking it. Then click on the HV Analysis button. You can tweak your analysis setting here depending on your server configuration. I will leave everything here as default, and I will check the directional HV analysis checkmark. Click OK to proceed. On the top left is what is called the horizontal to vertical ratio, or H/V curve. This curve represents the difference between the amplitude of the horizontal wave and the vertical wave, which are plotted on the bottom left, called the spectral plot. As you can see, the horizontal waves are marked in green and blue, representing the north, south, and east-west components, while the vertical wave is marked in purple. One observation we can already make from those two plots is that there appear to be two major seismic interfaces or impedance contrasts in the data, one at around 5 Hz and another at around 56 Hz. At around 5 Hz, the gap between the horizontal curve and the vertical curve is the greatest, which is why we see a peak in the H/V ratio plot. The two plots on the right are data quality control tools. The top right plot is called the stability plot, and the bottom right plot is called the directional HVSR plot. I'll start with the directional plot first. From this plot, we can see that there are two dominant frequencies in the recordings, one at around 5 Hz and another at around 50 or 60 Hz. For the 5 Hz signal, there appears to be weaker response at around 90 degrees azimuth, while for the 50 Hz signal, the response appears to be weaker at around 110 degrees azimuth. There are several factors that can affect this plot. First, the location of the source signal can strongly influence the directional response. For example, if the wind is blowing consistently from one direction, you may observe a directional bias in the higher frequency range due to wind noise. Additionally, geological anisotropy can also bias the data in certain directions. For example, if the device is placed on a linear fractured medium, and those fractures introduce seismic anisotropy, there may be weaker signals in the fractured direction because the seismic wave loses more energy traveling through the fractured material compared to the surrounding solid media. Now we turn our attention to the top right stability plot. Similar to the other plots, we can see two dominant signals, one at around 5 Hz and another at around 50 Hz. If we focus on the 50 Hz signal, we can see that it becomes relatively quiet for about 15 minutes, roughly between the 12-minute and 35-minute marks. This may suggest that the signal is related to human activity. The next thing I would like to show you is how to remove part of the trace and analyze it. Say, if I would like to see the HV analysis with consistent signal at the 50 Hz, I can trim the time when this signal is not active. To do this, I will need to select two windows, before 12 minutes and after 35 minutes. I will first enlarge the stability window to make the selection easier. To select the window, press and hold your mouse at where I want to start, drag to where I want to stop, and release my mouse. To select multiple windows, I will hold my Shift key and do it again for the second window. To apply the windows, click on the third button from left. Another way to check the quality of the trace is to look up the statistics of the trace. To do this, select the trace you want to access and then click on this button and find the analysis you want to access and double-click on it. This will promptly open a Word document on your computer, and we can scroll down to the last page of the report to look at the statistics. I will not go into detail of what each stats means, but I will reference a report by the Sesame European Research Project that discusses these stats in detail. You can find the links to this paper in the descriptions below or search up with the keyword Sesame and HVSR. Shown on the screen is a screenshot of the HVSR data modeling menu. Once we're satisfied with the quality of the trace, the next step is to interpret what these peak frequencies represent in the subsurface. In HVSR analysis, the dominant resonance frequency can often be correlated to the depth of a major independence contrast, such as the interface between soil and bedrock. To do that, we need to relate the resonance frequency to the shear wave velocity of the material. The equation used to estimate the depth of a layer is shown here. F naught is equal to Vs over 4 times h. Here, F naught is the resonant frequency, Vs is the shear wave velocity, and h is the depth or thickness of the layer. Once we determine the peak frequency from the HV curve, we still need an estimate of the shear wave velocity in order to calculate the depth accurately. One way to estimate shear wave velocity is by using other seismic methods, such as seismic refraction or reflection surveys. More commonly, HVSR data are collected at a location with a known depth to bedrock, such as near a borehole. In that case, you can determine the resonance frequency from the HVSR data and use the borehole log to solve for the shear wave velocity. That estimated shear wave velocity can then be applied to other sites with similar geology. That marks the end of this video. Thank you for watching. Andy from Lithogen.